Okay, thank you everyone. I think we'll get started now. I'll just remind you that we've got a live recording of this, so if you wish to look at the seminars again at a later date, the link is just there. And also at the end, when we come to talk about, if you have any questions, if you could just wait till the microphone is given to you so that your question is recorded. So welcome everyone to the first in a series of seminars by PhD students that are supported by the Goyder Institute. Before we commence, I'd just like to acknowledge the traditional owners. The Goyder Institute for Water Research acknowledges that we're meeting on the traditional country of the Kaurna people of the Adelaide Plains. We recognise and respect their cultural heritage, beliefs and relationship with land, and we acknowledge that they are of continuing importance to the Kaurna people living today. I'll just briefly give some background about the Goyder Institute. The Goyder Institute for Water Research was initiated in 2010, and it's a collaboration between the state government through the Department of Environment, Water and Natural Resources, CSIRO, and the three universities, Flinders University, Adelaide University and University of South Australia. The aim of the Institute is to support world-leading water resource policy and management in South Australia through scientific research, and in doing so to underpin sustainable development of the state's valuable water resources. The Goyder Institute for Water Research awards PhD supplements to outstanding candidates from each of our university partners to undertake research which will build South Australia's capacity and to facilitate knowledge exchange and collaboration. And so far the Goyder Institute supported 25 PhD students. So this seminar series is a forum for showcasing their research and also to spread their research to a broader community beyond the university sphere. Today we have three speakers. We have Eva Bay from the University of Adelaide, Michael D'Amato from University of Adelaide also, and Robert Andrew. The format that we're going to follow is all three speakers will present their work and then there'll be questions at the end. So if you can just make notes and we'll ask questions at the end. And again, as I mentioned before, if you could just wait until someone gives you the microphone before you ask your question. Could everyone please turn off their mobile phones? Thank you. And we're just going to start first of all with Eva. Eva is studying at the University of Adelaide under the supervision of Professors Graham Dandy and Holger Meyer. And the title of her seminar is up there, Optimal Sequencing of Water Supply Options at the Regional Scale, Incorporating Alternative Water Supply Sources, Multiple Sustainability Criteria and Uncertainty. So if you could join me in welcoming Eva. Thank you.
Testing?
Yep. Off we go.
Good afternoon everyone, my name is Eva and today I'd like to present you my research topic which titled Optimal Sequencing of Water Supply Options at Regional Scale, Incorporating Various Water Supply Sources, Multiple Sustainability Criteria and Uncertainty. So first of all, I would like to introduce the key concept of my research, which is sequencing. So sequencing of water supply sources involve choosing which water supply sources to implement at a specific stages over a defined planning horizon. So this allows water supply sources to be introduced to the system when they are required. So this will reduce the redundancy and therefore the cost associated with the system as well. So as a result of increasing population, climate change, climate variability, and the consideration of multiple sustainability criteria, the problem of sequencing of water supply sources has become more complex in recent years. So first of all, due to the increasing demand and reduced water supply, reliability of water supply, there is a need to consider recycled water, desalination plant, or desalination plant as additional water supply options. And in addition, The need to develop sustainable water supply system has become increasingly important, requiring consideration of multiple sustainability objectives. So now we're not just looking at the economic cost of the system, but we also need to consider the environmental and social criteria. So adoption of sustainability criteria also requires the consideration of extended planning horizons, which is 50 or 100 years. And this will promote increased uncertainties such as population growth, climate change, and technological changes. So furthermore, there is a large level of uncertainty in the supply as well due to the climate factors. So to address these challenges, I would like to present you a robust and adaptive sequencing approach, which utilizes multi-objective evolutionary algorithm coupled with the water supply system simulation model to identify a series of sequence plans that represent the optimal trade-off between the selected objectives under deep uncertainty for the extended planning horizon. And this proposed approach, it's applied to the case study of the Southern Adelaide water supply system to demonstrate and test its utility. So it should be noted that the aim of the case study is not to solve the Adelaide water supply system problem. It's just to demonstrate the approach. So this is a simplified case study based on the Adelaide Southern system in year 2010. So there's existing water supply options such as Happy Valley and Maipunga reservoirs, supply from the River Murray, and the potential water supply option we consider in the case study is the household rainwater tank, stormwater harvesting schemes, and desalination plant. So the objective of the case study is to minimize the present value of costs and also to minimize the present value of greenhouse gas. And decision variables are the timing to implement new supply sources and also the time to expand implemented desalination plants, which means if we are going to implement desalination plant in the first stage, so the following decisions that are variables would be the timing to expand or not. And one of the decision variables is the capacity of the rainwater tank. So the uncertain variables we consider, it's the future population growth and also the climate change impact in terms of rainfall and evaporation. So this case study is done for two assumed realities. So each of the reality will consider 7 different possible scenarios. And the planning horizon is 50 years with 10 years of staging interval, which means we're looking at 50 years plan, but we're making decisions for every 10 years. So this proposed approach consists of 3 major components. So the first one is to identify a diverse portfolio of optimal water supply sequences for 50 years using a scenario-based multi-objective optimization model. And then the second component is to assess the performance of the portfolio of the optimal sequence plan in terms of robustness and flexibility over the current staging interval, and also look at the variation of the cost and greenhouse gas for the whole planning horizon. So we will actually looking at the robustness and the flexibility for the current 10 years, even though the plan is actually optimized for 50 years. So I'll explain that in detail later on. And the third component is to select which water supply sources to be implemented at a current staging interval. So we are planning for 50 years, but we don't want to lock ourselves for the future 50 years. So what we do is we actually assess the robustness of the system and also the flexibility of the system for the current 10 years. And then we decide which supply options to be implemented and locked in for the subsequent stages. So for the next decision stage, we'll do the same thing because uncertain variables like future population growth and rainfall, they will change over time. So for the next staging interval, we will actually plan for another 50 years using a new set of projected population growth or the rainfall or evaporation data. So so this, the robustness of the system is actually calculated based on the reliability of the supply and also the vulnerability of the supply. So reliability of the supply is a measure of how frequently the supply capacity equals or exceeds the demand. And the vulnerability is the percentage of the maximum annual supply shortfall over the planning horizon. And the robustness of the supply is the fraction of scenario when the system reliability is greater than 95% and the maximum vulnerability is less than or equal to 27% of the demand. And then the flexibility of the system is actually the fraction of the scenario for which group of sequence plan that have the same augmentation options at the current stage. Means if we're considering 10 uncertain scenarios, so that group of water supply options appear for all of them, then they will have flexibility of 1. If they only appears in one of the scenarios, means they have the flexibility of 0.1. So 1 means it's more flexible, 0.1 means less flexible. So this is the first step of the sequencing process. So the first thing we need to do is we need to define the uncertain variables and their range. For the case study, I'm looking at future population growth, rainfall and evaporation. So I need to define the range as well. And then I'll need to define the scenario. The scenario is actually the combination of the selected uncertain variables. So the range and the scenario should be selected to reflect the best current knowledge in relation to the possible changes of the uncertain variables over the planning horizon. And then the optimization process will be repeated for different scenarios to generate different sets of the Pareto front solution for each scenario. So for the case study, we're looking at 7 different scenarios for each reality. So we'll get seven different Pareto front solutions. And this optimization, we're actually looking at 50 years planning horizon. So the next step is we need to assess the performance of the sequence plan. But this step, we're only looking at the current staging interval, which is 10 years. As I said, we don't lock ourselves for the future 50 years. So what we need to do is we want to know what we planned and what should we actually implement for now. So the first thing is to assess the robustness and the flexibility for the groups of optimal sequence plan with the same unique solution. And then we'll have to look at the variation in terms of cost and greenhouse gas, which is our objective function, over the entire planning horizon. So if we go back, if we look at P1 actually conceived a plan where rainwater tanks should be implemented in year 2010, followed by stormwater schemes in 2020. But the next step, we're only looking at the rainwater tank implemented in 2010. So what we need to do is we need to assess the water supply sources, which is chosen in 2010. But the range of the cost and greenhouse gas we're considering it's for that whole 50 years. All right, so the third step is to select the water supply options to be implemented based on the performance assessment. So this is the value path plot that I used to actually to compare the trade-off. So for this case study, I'm looking at the range of the costs and also the median of the costs and greenhouse gas as well, and that is for 50 years. Then the robustness and flexibility is for every 10 years. So this process that I just mentioned will be repeated for every decision stage, and this is because the uncertain variables change over time, so that the scenario that we consider might change as well. So we need to actually do the whole process from stage to stage. All right, if we look at the results I've got here, so this is for the plan in 2010. So generated for 2010, you will see there's 6 unique solutions as shown in the table. So the first one is, because we're considering 7 different scenarios, so among the 7 scenarios, some they have more severe population growth and climate change impacts, some they have like less severe. So you might find P1, nothing is actually required for the first stage. And P6, you will need 2 stormwater harvesting schemes. So if we look at solution 1 and 2, they actually perform better if we just look at the median of the costs. And solution 4 and 6, they have high level of robustness, but they have very high median of costs. So there's a trade-off there. And sequence plan group 3 and 5 tends to perform well across all the performance criteria. So they clearly outperform all other groups in terms of median and range of the greenhouse gas. But you may find it, in terms of flexibility, they're actually at the lower end, but there's a trade-off that if the flexibility is slightly lower, but you get a higher robustness. So for this case study, P3 is actually selected. So Brown Hill and Cassie Creek stormwater schemes is actually selected to be implemented in the first stage. And this option will be locked in for the subsequent stages. So for when time is equal to 2020, the Brown Hill and Cassie stormwater schemes would be the existing option to start off when you plan for the next 50 years. So this process is repeated for 5 decision stages, and end up we've got this 50-year adaptive plan. So as I said, this case study is actually carried out on 2 assumed realities, and each reality contains 7 different scenarios. So for the first reality, it's not that severe. So you must see 2 plans. There's similarity, which is 50 gig desalination plants actually require, and also the Brown Hill and Cassie stormwater schemes actually implemented in the first stage. But the only difference is for reality 2, desalination plant is actually implemented earlier. And 2 more stormwater schemes actually require in stage number 3, which is 2030. And for reality 1, it's just 50 gig desalination plant implemented in stage 3 would be able to actually sustain for the up to 2050. And if you look at the cost, the present value of cost for plan for reality 2 is 1.5 times than the first one. And the greenhouse gas is approximately 1.2 times of the plan of reality 1. So in conclusion, a robust, adaptive, and multi-objective optimal sequencing approach for urban water supply system under deep uncertainty is introduced. And this approach is actually applied to the case study of Southern Adelaide water supply system to actually demonstrate and test the utilities. Then the proposed approach is actually adaptive to changing conditions while optimizing for extended planning horizons. And also multi-objective, satisfying water supply security constraints along the planning horizon in highly uncertain planning environment. Thank you.
Thank you, Eva. We'll continue with the presentations and then we'll have questions at the end. Okay, so our next speaker is Michael DiMatteo, who's also at the University of Adelaide and also has supervisors Professors Graham Dandy and Holger Meyer. And the title of his seminar is Optimisation of Water Sensitive Urban Design, Conceptual Design for Water Quality Improvement and Reuse.
Through that? Yep, that's working. Great. Great. Okay, so thank you for that. So my research probably has a little bit different approach to Eva's research, but I'm also using optimization algorithm to deal with water resources problems. So the title of my talk is Optimization of Water Sensitive Urban Design, Conceptual Design for Water Quality Improvement and Reuse. And our supervisors, Professor Graham Dandy and Professor Holger Meyer. A little bit of an outline of my talk today. I'm going to go into some background of what problem we're addressing in water-sensitive urban design, some of the research objectives and challenges that we're facing, covering the water-sensitive urban design optimization approach that we've developed, and how we've applied that to a case study and some of the results of that case study. And then we look at some of the conclusions from the case study and some of the current and future work that we're doing in the research. So a bit of background about the concept of water-sensitive urban design. You may have heard of it before. If you can imagine that we have some unused farmland here at the moment, when we have a rainfall event like today, the behaviour of the runoff of that rainfall is going to be radically different to when we decide to get some more value out of that land and have provide a housing development on that land. So when water now lands on that catchment, it's going to be running off a lot quicker and a lot higher volumes, and it's also going to be introducing pollutants into our natural environment. So to deal with some of these problems, the sort of evolving field of water-sensitive urban design tries to get as many benefits out of the design of our development, for example, to return those flows that have been altered by the development back to the natural flow regime, removing some of those added pollutants, protecting our property through flood control, stormwater harvesting and reuse, and also seeing if we can provide higher values for amenity and community benefits through that design. So there's a lot of objectives that we're dealing with in water-sensitive urban design. And we strive to achieve those objectives through the implementation of what are called best management practices. And you might be familiar what they are. So under the umbrella of best management practices are wetlands, rain gardens, swales and curb and gutter, sediment ponds, rainwater tanks, and gross pollutant traps. So particular best management practices are better at achieving certain objectives, and some of them can achieve your flood control and treatment objectives as well. And a brief introduction to the optimization approach we're using. So engineers and planners will go out and have a look at that development site, identify what are the appropriate best management practices that we can possibly use on that development in the previous slide. And they'll define the constraints of what treatment practices can we use and in what order. And so given those constraints and also the objectives that they want to achieve, we can take those objectives and constraints and implement them into our model. And so the way that the model works is it'll generate one possible solution to that problem, test its feasibility through a simulation model. So in this example, we're using eWater Music for treatment performance. Evaluate the performance of that model, and then feed it back into our optimization algorithm, which I was trying to think of a good metaphor for what it does. It's sort of like a self-driving car. So it has some intelligence, some artificial intelligence, and it wants to search through the millions of possible combinations of those solutions to troll through the infeasible solutions, troll through the solutions that are feasible but don't perform very well, and then try and find the optimal or the most efficient solutions with respect to treatment performance, flood control, and our other benefits. So there's been some of the challenges that the researchers are addressing is how engineers will use these optimization approaches in practice. And we deal with some problems of perception of what the optimization approach can do and what it can't do, what it is, what it isn't. So you might be familiar with the internet memes that deal with like how different people perceive us or what we do. So for example, environmental scientists, their friends might think they do something, their boss thinks they do something a bit different. I tried to emulate this with what we're trying to achieve, or what we face in water-sensitive urban design optimization. So as a Worcester optimization PhD researcher, I'm looking at computer programming on a daily basis, linking that with a simulation model, and looking to get sort of accurate evidence-based results through that process. And some engineers see that the optimization algorithm, because it's got its own artificial intelligence, they see that perhaps they don't have much of a place in that procedure. So they see it as the whole approach is like a self-driving car, and they wonder where the place for their experience and judgment in designing these systems has inside of this computer algorithm. So the research addresses that issue of implementing engineering judgment into the optimization algorithm, and so what a PhD candidate really thinks it is. So we recognise that it's sort of a very powerful technology that the average engineer should have a grasp of, just like Prometheus thought he should bring fire down for the humans to use. Not to be too pretentious about what my research is, but and yeah, so we recognise the tool and it should be available in consulting on your day-to-day designs. Yeah, and then we come to another hurdle is the runtime. So you can imagine trawling through millions of simulations can take days to arrive at optimal solutions, which is okay when you use research facilities, but for consulting, your consulting hours, billable hours become a problem. So what we're aiming to do is take our engineering judgment and rules to see if we can affect the way that the optimization algorithm searches, so it searches in a more efficient way using that human sort of intuition and arrive at solutions in a shorter amount of time, so we get lower runtime. So what water resources decision makers think that optimization is? I guess they're more concerned with, okay, what results does this approach give us? They're less concerned with the way that it arrives at solutions, more concerned with the solutions themselves. And I think what optimization approach really strives to achieve is, for example, if you say you put a couple of destinations in Google Maps and you want to get from A to B, you want to get from your pre-development situation to a post-develop or a developed situation where you have your water-sensitive urban design layouts in front of you. Google Maps will give you a few different ways you can achieve your objectives. Okay, so an optimization approach strives to give the decision maker a few different ways of doing things, considering that there's multiple objectives. So getting into the simulation model that we're using, so this is linked with the optimization algorithm, and it'll simulate thousands of runs with this model. So music, I think it's an industry standard, and we can assess the water quality, quantity, and life cycle cost by changing the layout. So what best management practices are we going to use, and where in the catchment are we going to have them? The surface area, extended detention depth of some of the devices, and other parameters there we can change. So as far as how it's constrained in formulating solutions, I've sort of trawled through the WSUD engineering procedures to make sure the best practice procedures are implemented into the optimization approach. And we've also discussed with consulting engineers on how they approach the problems to try and garner some of that engineering judgment or engineering knowledge and place that into little rules. For example, the percentage the percentage of surface area to catchment size might be indicative of what the optimal size of a wetland might be. And yeah, so through the problem formulation, so just deciding what options are on the table, and also the constraints within the algorithm is where we've implemented that judgment. So the case study itself, it consists of a new housing development where there's essentially 6 nodes. So if you have 1, 2, 3, 4, 5, 6 nodes with some options for, so there's an upstream either detention basin or wetland. We can have rain gardens or not, and also there's an option for a wetland downstream as well. So that's, so we have 4 subcatchments around about 33 hectares of roof. And in this particular case study, we have 24 decision variables. And if we multiply that out over the 6 nodes and the different parameters we're altering at those nodes, it works out to about 7 quadrillion possible combinations. So a lot of those combinations are going to be infeasible, and we would never consider them. So they're cut out through our constraints. Then there's going to be a lot of feasible solutions that don't perform very well. And the optimization algorithm will take them on board and then sort of try and search past them to find optimal solutions that work efficiently. And we're looking at life cycle costing there, a couple of data points there, and continuous simulation, which means that there's runtime is going to be an issue. Okay, so the intention of the case study was to look at the trade-off between 3 objectives. The life cycle cost of the system we're implementing, how much treated water can we get out of the system for reuse purposes, and also how well can we treat our runoff. So this is jumping straight into what the optimization sort of spits out, or what the results of the optimization are. So each point on that surface there is what's called a Pareto optimal solution. So each one is a concept, a potential concept solution that we could put into practice with its own little features and combination of parameters. So this was done on a desktop computer, so what a consultant might have access to, and around about 6 hours of runtime. And so we can have a look at the projections of these on those between life cycle cost and treatment, and life cycle cost and reuse capacity. So that projection there, we have I've just identified a couple of solutions to look into in further detail. The solution that gave us the highest capacity for the comparatively lowest cost, and also the lowest cost solution, which incidentally gave us the lowest capacity, potential reuse capacity. And also looking at life cycle cost and pollutant removal. Again, our lowest cost solutions give us the lowest treatment performance, and our highest sort of Rolls-Royce solution gives us a very high treatment at sort of a high cost. I could have chosen a solution that has a little bit less treatment, but you could be saving some money there as well. So we could have also picked that solution. So just looking at the what those little dots look like, what those points on those charts look like. So if you're looking at a low reuse, low cost system, it opted for a sediment pond upstream of a wetland with a small surface area and large extended detention depth to capture that stormwater. The highest reuse opted again for a sediment pond and a wetland, but this time with a larger surface area, which can be expected. Lowest treatment, lowest cost is opting for a similar setup, but with a small surface area. But then when we get to that really high treatment and high cost option, it's gone for the devices that provide a lot of treatment value. So wherever you could have a rain garden throughout the catchment, it opted for that. And it also opted for an upstream wetland treating water and a downstream wetland as well, with a medium surface area. So yeah, once you have these solutions available to you after the optimization results, the idea is to go through and analyze what trade-offs we get. So perhaps we weren't having extra rain gardens wasn't actually worth the extra treatment and extra cost. So if we finish with a business case for adopting an approach like this in a consulting setting, so if, for example, if you have your approach set up and you can, once you've done your site analysis, you've got your options available, pop them into the optimization framework, run it for say 24 hours of simulation. If you are able to achieve a 10% improvement in cost through this optimization process, and your average system is $4 million over its lifespan, you can achieve like a $400,000 present value saving through undertaking an optimization approach like this. So a little bit about the current and future work for this research. We're looking at, again, incorporating more of that engineering knowledge to help that self-driving car find solutions in a more efficient way, so get our runtime down. Address some of the complexity. So I know in the new water-sensitive urban design guidelines, they're looking at more continuous simulation for different risk analyses. So that's going to be incorporated into the framework. And looking at a case study similar to what Eva was talking about, so sequencing these best management practices over time to map the way that the housing development would be built in stages over time. So trying to maximise the benefits over a longer period. I think that's all I have for today. Thank you.
Thank you, Michael. Robert is next.
Just pop it in your pocket. I think it's the easiest. My pocket's not very big. There we go. Let's open it from the desktop. Oh, there we go. That one.
Cool, thank you. Yes, hello, my name's Robbie, and I'm a Goyder-funded PhD student from Flinders University, and I'm going to talk about something completely different to Eva and Michael. So basically I'm going to be talking to you about a new method for measuring total water storage, and I'm more towards the start of my PhD than the end, so you're going to see more concepts and less results, but hopefully it'll still be exciting. So to start off with total water storage, basically we define that as the water being stored generally as surface water, but depending on the case, sometimes some groundwater as well, and I'll explain a little bit later why it sometimes includes groundwater for this method and sometimes doesn't. Obviously in a place like South Australia where we live, we have issues with water availability, so knowing how much water storage we have is quite important. And water storage is usually calculated and not measured. So the way that total water storage is usually calculated is with this equation, basically stating that the change in storage, sorry, not total storage, change in storage, is your precipitation minus evapotranspiration minus stream flow. So basically water inputs into a system minus water outputs into a system. And to put this equation into place, we need to know quantities for precipitation, evapotranspiration and stream flow. And these can sometimes be hard to accurately measure, particularly for, say, evapotranspiration, which is almost always calculated. And that means that these quantities are sometimes based on assumptions, and there's a potential for big errors. I like to try to explain the concept a little bit in the way of how a change in storage in a human might happen. So if you think we have inputs and minus outputs, that gives us, our body, a change in storage. So for example, inputs might come in the way of tacos, strawberries, coffee and carrots, and the outputs might, energy outputs might leave your body in the way of, let's just say, exercises. And say hypothetically I wanted to know my change in storage between today and next Thursday. I wouldn't add up all my inputs and then add up all my outputs and do the maths and figure it out. Instead, I would probably jump on a set of scales tonight and jump on a set of scales in a week's time and look at the difference. And believe it or not, we can do the same for water over a large area. So the way that we can do that begins with the concept of mechanical loading. So if you see this very conceptual cross-section that I have here, it basically shows some unconfined aquifers and soil, followed by a thick confining layer and a confined aquifer. And what this confined aquifer can do is act essentially as a giant scale. So mechanical loading is basically the process of when there's vertical stress applied at the Earth's surface, this can get carried down through to a confined aquifer where the stress is split, you can see here, at the confined aquifer layer, somewhat between the fluid in the confined aquifer and also in the grains of the confined aquifer. And so the force being put down on that confined aquifer is basically taken up half, not exactly half, in part by the fluid pressure and in part by the aquifer skeleton. And that can result from any mass, so not just a hydrological mass on the surface. And yeah, it's basically the sedimentary compression which causes this pressure change in a confined aquifer. Oh, there's some weight on the surface. So the performance of mechanical loading is affected by the solid properties of the aquifer that you're measuring in. I assume everybody here knows that a sponge is pretty compressible, and pumice, which looks a bit like a sponge, is quite rigid. So say we put the same load on a sponge and on some pumice, and say also that we build some walls around them so that they're confined and no water can escape. When we put this load on the sponge will compress and the water pressure inside will increase. Whereas when we do this on the pumice, the water pressure won't increase so much because a lot of that load or a lot of that stress has been taken up by the pumice itself. I guess if you can imagine, if you stomp on a sponge and stomp on some pumice, the sponge has got a squash and the pumice isn't. So if you have a very compressible aquifer, when you have some mechanical loading on the surface, you'll see a bigger response in the fluid pressure, and if your aquifer isn't so compressible, then you'll see a smaller response in fluid pressure. This mechanical loading concept was first discovered in 1939. There's a nice paper by Jacob, 1939, which shows this. He was literally out measuring his borehole next to a train station rather, and a train pulled up to the station, and he noticed that his fluid pressure in his confined aquifer shot right up, and then you can see there the fluid pressure dispersed away from where the borehole was. And then moments later, the train pulled away, and there was some unloading, as we like to call it, and the fluid pressure went down and then slowly returned to a normal steady state condition. So that was 70 years ago that the mechanical loading process was first identified. So I said that I was going to tell you about a new method for measuring water storage, and that method goes by the name of a geological weighing lysimeter. So some people might be aware of a regular weighing lysimeter, which is essentially, I guess you could say, if you've got a pot plant and weighed it in the morning and then weighed it again in the evening, the difference in its mass would be the water loss through evapotranspiration. This is the same concept on a much larger scale. So a geological weighing lysimeter is basically the name we give to any deep confined aquifer that we use to measure water storage above it by looking at the pressure changes in that confined aquifer. And those pressure changes come about as a result of mechanical loading at the surface. And this is where I said that when we talk about change in storage, it includes surface water and sometimes groundwater. For this method, it depends on the confined aquifer that you're measuring. Basically, it's going to measure the mass of everything above that aquifer. So if you measure an aquifer with 3 aquifers above it, you're going to be measuring the mass in those aquifers as well as the surface. Whereas if you measure a confined aquifer with only an unconfined aquifer above it and then some surface water, that's all the measurements you're going to get from that aquifer. To be a good geological weighing lysimeter, aquifer needs to be well confined, and like I said before, its performance is affected by solid properties of the aquifer. So I have a small amount of data to show from the lower southeast. This was from a seasonal wetland and from quite a shallow confined aquifer, I think only about 17 meters deep. So you can see the lines in blue represent daily rainfall, and the red line is the fluid pressure in this confined aquifer, and this is over a period of about 2 years. So there's a few interesting things you can notice. If you look at where some of the larger rainfall events are, you can see quite clear loading responses in the confined aquifer pressure, which shows this is quite a good geological weighing lysimeter. You also see seasonal trends. Hang on, let's not talk about that yet. Let's draw this line here. So you can just look at this single graph and see that in this year, 2007, we had a larger amount of water stored in this area than 2008 because the fluid pressure, which rose from loading, was higher. And this aquifer, as far as we can tell, has no leakage or no flow in and out of it. So all of this change is simply from mechanical loading. You can also see with these green lines, which don't know how well they showed up, that the evaporation rate at the start of 2009, over a few months, was quite a bit higher than at the start of 2008. So just from this one simple graph of some confined aquifer pressure readings, we can tell quite a bit and very easily. So that graph is nice to look at, but it's maybe not essentially that useful in that form because we can't get any type of quantities just from looking at that graph. So basically just to tell you that you can break that data down further and actually convert what you see in that graph into changes in mass and volume, which obviously are a lot more useful. So I have a background in my undergrad and honours in surface water and groundwater, but this method basically is a combination of those two things as well as a lot of geomechanics, which I know nothing about. Well, I know a little bit about now, but a year ago I knew nothing about. So there's a lot we know and a lot we don't know, and a lot that hasn't been linked. And so it's quite important that we try to do some modelling of these systems to help further understand how it all links together. Something that I'm really interested in finding out through modelling is the temporal and spatial resolutions of a pressure wave. So if you look at this cross section of, this is straight through the middle of Adelaide actually, from the hills down to about Semaphore. Let's say I'm measuring in this borehole, you see that mouse over here, and it rains here. Say we have 10 millimetres of rain here one day, and the next day we have 10 millimetres of rain over here. How will that look different in this borehole? How much longer will it take for the pressure increase in the confined aquifer to get to this borehole from this rainfall event compared to that rainfall event? And is it going to be dampened somewhere along the way? They're all things that we don't know. So these are things that we're trying to use some modelling to figure out. I've got a very conceptual and basic model here to show you, which I've made. This is using a program called OpenGeosys, which is a thermo-hydromechanical chemical model, basically everything you could ask for, from Germany. And as far as I know, I think I'm the only person in Australia that uses it. So in May, I actually went over to Germany to talk to the developers and learn a bit about it. So what I'm going to show you with this model is basically, imagine this is an aquifer. Imagine we live in a world with perfectly, rectangular aquifers. And in this 20% of the aquifer over here, it's going to rain for a little while, for a few hours. And then that rain's going to stop. Now you have to remember that when rain stops, the mass is still there. It's just not coming in anymore. So we're going to see some mass gradually build up from this rain, and you'll see a big pressure increase where it's raining. And then once that stops, the pressure will dissipate until we get into some type of steady state condition. So hopefully that will run. There we go, raining, 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 and it stopped raining, and everything's starting to balance out nicely. Now, that in itself might not be that helpful to show you right here, but hopefully it gives you a better understanding of what the method looks like in a conceptual sense, and also the type of things that we can do with this model, which I guess we're still in the early stages of trying to figure out because it's all written in German. So there's some advantages of this method. First of all, and maybe most importantly, is you're looking at a real measurement, so no estimations or very few estimations or interpolations of data. This is just like weighing, storage change basically. Because we use high resolution pressure transducers for this, you can set them to record at any interval you want, so you can have 2-second data, 2-day data. It's very flexible. Also very easy to measure, and data's quite easy to interpret. It's relatively cost effective. Some limitations of the method is that it's likely to get lots of noise in your data, and you need obviously a decent aquifer to apply it to, so it's not applicable everywhere. You get a change in storage, so if you have a loss in storage, you can't tell if that's from evapotranspiration or from streamflow as such, you just know that you have a loss. So it depends on whether that's what you're interested in or not. Loads aren't always hydrological. There's a great story of sort of the pioneer of this method in New Zealand who was measuring his borehole, and he was looking at the data and it went up quite quickly and he couldn't figure out why. So he went to his borehole and there was a school of cows over it, and that's what caused the loading. So if you can imagine, if you're looking at a borehole, say next to the airport, every time a plane lands, you might see crazy things happen. And also the method's not yet well established. It's still very much a work in progress, but hopefully it can one day be used a bit more mainstream. So just some future work that I'm looking at over the next couple of years. I'd love to try apply this method around the CBD because generally it's only been applied in ideal settings before with not much noise at the surface. So I'm hoping that I'll be able to apply it in the CBD and then filter out some of the noise caused by traffic or whatever it may be. Obviously, we'll do some more complex modelling. I'd love to replicate that train experiment I showed you originally. And also, I'm slowly finding out through data collection that there's some other things that mechanical loading can tell us. For example, I discovered a couple of boreholes that were blocked just by the way the data looked. So that's interesting. A couple of acknowledgements, and thank you.
Thank you, Robert, and I should apologise that I forgot to mention that your supervisors, Dr. Guadi Guan and Professor Oki Bartalan, who's with us today. So if you could join me in thanking our speakers, and then I'll open the floor to questions. So thank you. So does anyone have any questions of any of our presenters? Well, I might start the ball rolling then. And I just wanted to ask Michael, how is this research different to other optimisation approaches that deal with water-sensitive urban design?
Yes, thank you, Danny, for that question I wrote. Yeah, so I think probably the key takeaway from my approach today was that I'm trying to address those issues of those barriers to engineers actually adopting these approaches. So there's that preconception that, okay, this model is going to do all the work for me, and I'm not going to have a place in deciding what solutions get implemented. So taking some of the engineer's intuition and judgment and coding that into the algorithm is hopefully going to break down that barrier. And also through implementing those judgment rules, it's actually going to speed up the process. It's going to make the algorithm find optimal solutions a lot quicker. And that was also a barrier. So the runtime in consulting is a problem. So yeah, this research here is addressing specifically those runtime problems, which have been problems with overseas in other models, optimization models.
Probably more of a comment than a question.
Yep.
One of the issues I think would be interesting would be the discharge processes on your system when you actually look at real systems.
Mm-hmm.
But the other, the model you're looking at reminds me of Wellington in New Zealand.
Yep.
Has a confined aquifer overlain by an unconfined aquifer which is stream-fed recharge, and then actually extends out under Wellington Harbour. And there's an island in the middle of the harbour with a bore into the confined aquifer.
Oh, okay.
So it's actually a very good possible case study looking at obviously the unloading and loading effects of tidal movements.
Yep.
So if you're looking for another comparative case study that might be worth, and it's well instrumented by the Wellington Council for their water supply, it might be worthwhile having a look at that as an alternative option, and it might be another good case study example.
Yeah, well, it's sort of interesting you say that because, I mean, like you say, you get tidal influences all the time, as well as earth tides and barometric fluctuations. But one of the ideas I've had was to find a nice borehole either near a lake or a river or something like that, and try and measure the whole lake or river. But yeah, certainly if there's a borehole within something like that, I think that would be quite interesting. Yeah. Yep. Thanks.
Yeah, I've just got a question for Eva about the scenarios that she used to develop it. I'd just be interested if you can tell us a bit more about what each of the assumptions, or roughly how they're categorised down into each of the 14 scenarios.
Oh, okay. For the case study, so we just assume 2 realities. For each realities, we actually have 7 different scenarios, so it's from 1 to 7. So 1 is probably the possible best, so we'll have like very low population growth, and 7 will probably have like very severe, like high population growth with a very high climate change impact. So the population growth actually, the data actually taken from ABS. So with different rates of the migration and what else? The rate of the fertility. So so out of this, that 7. So and also the climate change impact. So the rainfall and evaporation data is actually taken from AussieClim. Yep. I can't actually give you a very detailed. Yep. So yep. So we actually purposely make the two realities to show the difference, how adaptive the both plants actually respond to the changing conditions. Yep.
Okay, thank you, Eva. Does anyone have any other questions? Neil?
One for Eva. Eva, when you're looking at things like stormwater, which is obviously not part of the potable water supply system unless you treat it to that level, did you distinguish between that in your scenarios, or just use it as an offset in terms of reducing demand on the network or something like that?
We actually, for the household rainwater tank and the stormwater schemes, we actually split them, potable and non-potable. So if we implement stormwater schemes to the system, so they will have first priority to supply the non-potable demand. So once the capacity actually is equal to demand, then the potable supply will actually back up. Yeah.
Is the price of the current settings for potable water supply pricing through SA Water, was that taken into account in terms of doing your cost scenarios?
For the costing and greenhouse gas calculation, I didn't actually use the actual price from SA Water, but because the case study actually used in 2010, so we just used the reports and the reports from the government, how we calculate the stormwater schemes, the price for the stormwater and desalination water.
I had a question for Michael. I just wondered whether you consider any other contaminants other than the TSS, TN and TP, and also in the model, do you consider the cost of the maintenance of sedimentation ponds?
Yes, for the second part of the question, I believe that's built into the music life cycle costing. Yeah, I've used that model at the moment. I was also going to look in a little bit more detail about adding perhaps advanced treatment costs and things like that. But yeah, clearing the sedimentation basins, I believe is included in the music life cycle costing model, but I can double check that. And as for pollutants, I've focused on those three major ones, and I left out gross pollutants because that tended to be it wasn't that you can just pop a gross pollutant trap in there and it won't affect the other processes. So,
Thank you. Does anyone have any other questions? Oki?
Also for Michael. In your whole approach, it's such an optimization approach. You use a model and lots of data, probably processes that go into it. And all of these parts have uncertainty. How do you know that the uncertainty doesn't explode in certain of the scenarios? Do you have some form of verification or validation of all of these scenarios?
Yeah, so we keep in mind the limitations of the simulation model itself. So I know they've identified that it's calibrated to certain pollutant concentrations and also certain detention times within wetlands. It gives a more accurate model of the processes. So I think engineers in practice do use those models with caution. So I apply the same caution. Like I'll set the parameters to the ranges that engineers will deal with, and also through the through the optimisation study, it's also necessary to undertake parametric analysis and sensitivity analysis for the parameters within the optimisation algorithm and also in the simulation model as well.
Okay, Michelle?
I've got a question for Eva. You think you're going to get out of it. With your assessment of cost and optimisation, I'm assuming that's using existing technologies, and just wondered whether you'd considered, a step change in technology that significantly reduced the price in one or more of the options, and what effect that would have in terms of optimisation and I guess the choice of options that you might implement over those scenarios.
Yes, due to technological changes, we probably in the future will use more renewable energy. That will probably save us a lot of costs. But for this case study, I didn't actually look at that yet. But this could be actually incorporated into the approach in the future, so that every decision stage you will need to include new unit costs or unit greenhouse gas due to the technological changes. So you probably might have desalination plant in the future will probably cost you less because we use renewable energy compared to stormwater schemes or household rainwater tank. But for my case study at this stage, I didn't actually incorporate that because I don't have much data available for now. Yep.
Thank you. Are there any other questions? No? Well, if you could join me in thanking our students. And I'd just like to remind you that the next seminar is here again, same time at 3 o'clock for a 3:30 start on August the 14th. So if you could let all your colleagues know, and we have already sent one flyer around already, and another one will come out in a week's time. Okay, thank you very much.